Good day, Dr. Fiza and Dr. Lam. Thank you for joining myself and the rest of us from Group 17 to present our title on the monetization of plastic waste for chemical production. The presentation will be divided into 8 sections as shown here. My name is Navin and I will start things off with a brief introduction on the topic. From the given question, 500,000 tons of PET and PP plastic are required to be processed together. The aim of this is to turn the plastics into syngas from pyrolysis and gasification process, followed by separation using a pressure swing adsorber. Next, the CO and H2 will form methanol, and the CO2 and CH4 gases will form acetic acid, which are the main chemical products for this project. Moving on, the main challenges faced with this project include the deciding method to handle the never-ending increase of plastic waste being dumped into landfills, according to an article by Wong and Jasmine. This method used should produce 2 useful chemical products that are marketable and profitable at the same time. Lastly, the following slide shows the main objectives for the process that emphasizes the design of an optimal system that prioritizes the safety and environment for the project formation as well as being economically viable.
Good day, I'm Sharvita Suryamurthy and I'll be further explaining on this literature review. So this literature review mainly focuses on the market survey on potential value added products from polypropylene and polyethylene terephthalate together with determining the plant location. So one of the value added product that we have chosen is the methanol. So methanol can be produced from the syngas formed from the gasification process of polypropylene and polyethylene terephthalate. It can be used in the production of hydrogen, used as solvent for extraction, washing, crystallization and precipitation in chemical industry. As we can see from the figure, it states the production and consumption of methanol in various regions around the world in the year of 2016. The overall production of methanol around the world is almost 65 million metric ton, whereas the consumption is almost the same. Also, the consumption of methanol is varied from region to another, and Asia Pacific has consumed the highest, which indicate a good base for methanol production for the region. The following bar chart shows the forecast for the demand of methanol around the world. According to IHS Chemical, the demand of methanol shows an increasing tendency from 2000 to 2020. Also, the current market price of methanol is $335 per ton. Next, the second value added product that we have chosen is the acetic acid. Acetic acid is widely used in many fields such as chemical reagent in the industries, antiseptic in medical use, seasoning in the food industry, and also a vinegar in the household uses. As from the bar chart here, it shows the comparison between the production and consumption of acetic acid from the year of 2000 to 2015. The demand of acetic acid has been increasing annually and the production of acetic acids has exceeded the number of demands starting in the year of 2010. And the following bar graph shows the consumption and revenue forecast of acetic acid from year 2015 to 2021. According to the IHS Chemical Report, it is forecasted that the global acetic acid market is expected to reach $13.65 by 2021. Currently, the market price of acetic acid is $374.38 per ton. After selecting the value-added products, plant location must be taken into consideration as the next characteristic. There are several factors that affect in selecting plant location. So for a plant that contains polypropylene and polyethylene terephthalate as the raw materials to produce methanol and acetic acid, factors like raw materials, markets and energy availability, climate conditions, water supply, site characteristics, flood and fire protection, community factors, transportation and waste and effluent water disposal facilities, labor supply, government policy, taxation and legal restrictions need to be considered in selecting a plant location. So to choose a best plant location, a comparison was carried out between the three plants where in Prai Pulau Pinang, Port Klang Selangor and Pasir Gudang Johor to build the plant for maximum efficiency by evaluating the weighted criteria from the scores assigned. The site's selection among the three nominated locations for the production of methanol and acetic acid from polyethylene terephthalate and polypropylene will be chosen based on the factors that have been mentioned earlier. Weightage ranging from 1 to 5 will be given where 1 and 5 represent the least and most important factors respectively. Scores will also be given in the range of 1 to 5 representing extremely poor, poor, moderate, good and excellent respectively as shown in the table below. As final result, the Port Klang in Selangor was chosen to locate the plant.
Good afternoon, my name is Nur Aida Karina and I'm going to explain for the process screening part. Now, let's proceed for the first process. For the first process for producing acetic acid is direct production from carbon dioxide and methane. This process uses catalysts such as zeolite. It is also known as hydrogenation of carbon dioxide. This reaction can be carried out using a dielectric barrier discharge (DBR) reactor. Both methane and carbon dioxide can be excited. Methane can be dissociated into methyl radical and hydrogen, and the hydrogen could easily stick to one of the oxygen atoms in carbon dioxide molecules. It has been analyzed that COOH radicals can be generated from CO2 in acidic environment. The acetic acid will be produced from the combination of group of COOH with the radical of CH3. For the second process for production of acetic acid is from methanol carbonylation. The commercial grade methanol was fed into the reactor. Carbon monoxide gas was purged into the reactor from pressure bottles. The ion ingress was minimized by passing through the carbon monoxide gas through the carbon filter. After the methanol has been produced, the methanol will go through the methyl carbonylation to produce acetic acid. So the advantages of hydrogenation of CO2 is it can reduce the greenhouse gases by using the carbon dioxide. The disadvantages of this process is low yield of acetic acid and high cost for catalysts. For the methyl carbonylation, the advantages is to reduce raw materials consumptions, lower capital costs and increase productivity. The disadvantages is high iodide environment and higher residual of iodide. Therefore, the method that has been chosen to produce acetic acid is the hydrogenation of CO2. The direct synthesis of methanol from CO and H2. A mixture of carbon monoxide, carbon dioxide and hydrogen are produced from the steam methane reformation process. The syngas is then converted into the temperature range of 250 to 300 degrees Celsius and pressure of 5 to 10 MPa with the use of CuO or zinc oxide or aluminum trioxide. With the water gas shift WGS reaction, the carbon monoxide in syngas is converted to carbon dioxide. The next process to produce methanol is the direct hydrogenation of carbon dioxide. Converting CO2 to methanol by direct hydrogenation is the most straightforward method, which involves the both heterogeneous and homogeneous catalysts. The following equations are the reaction which converts CO2 to methanol. This is the comparison between the two methods to produce methanol, which is the direct conversion from CO and H2 and the direct hydrogenation of CO. The advantage of direct CO and H2 is higher methanol yields due to the high amount of carbon available. For the direct hydrogenation of CO2, the simpler process with lesser equipment required, and the disadvantage is lower yield of methanol. Therefore, the production of methanol using CO and H2 seems more promising, especially with the higher yield of methanol can be achieved.
My name is Nirosha, and now I will explain about the selection of best process configuration. This is the first alternative for the process configuration. The plastic waste will first enter the pre-treatment process, which consists of conveyor belt, dryer, and crusher. The crusher crushes the plastic waste into smaller particles before they enter the syngas production phase. Here, pyrolysis is the first process where it produces high amount of pyrolytic oil and some amount of gases. The pyrolytic oil will then enter the gasification process in a gasifier, where main gases used for the production of methanol and acetic acid will be produced. These gases will be carbon monoxide, carbon dioxide, hydrogen, and methane. The product then goes through the cyclone for removal of char and ash. Next process would be the separation process, which occurs in the pressure swing adsorber. Each type of gas will be separated and absorbed through the adsorber before entering the respective reactors for methanol and acetic acid production. As for the second alternative, the plastic waste again goes through the pre-treatment, which consists of the same components, and syngas production to the same components, but here the difference is in the separators. As we used pressure swing adsorber in the first alternative, in the second alternative here we are using membrane separators to remove and separate carbon monoxide, hydrogen, carbon dioxide, and methane before they enter the respective reactors for production of methanol and acetic acid. For the third alternative, we can see that the plastic waste will go through the same pre-treatment process, which consists the conveyor belt, dryer, and crusher, but the difference is in the syngas production phase, where the gasifier is not here to produce gas, but the pyrolysis will be producing pyrolyzed oil and also gases at a very high temperature. The product then goes through the cyclone for removal of char and ash, and then through the separators, which is the pressure swing adsorbers, before methanol and acetic acid are produced through the reactors. Among these three alternatives listed, we have found that the best configuration process for production of methanol and acetic acid is alternative 1. This is because in alternative 1, pyrolysis occurs at an optimum temperature, which is not too high, as there is presence of gasifier. Gasification process has higher efficiency energy recovery, therefore it is advisable to use it along with the pyrolyzer to save energy. Pressure swing adsorber, which is used in alternative 1, is far more economical than a membrane separator, as membrane separator requires high maintenance costs. As for the manual mass balance calculation, the initial feed for this plant is 500,000 tons per year plastic waste. So we have decided to use 50% of polyethylene terephthalate and 50% of polypropylene, which is 250,000 tons per year each. Next, this chart shows the manual mass balance calculation method, which starts with conversion percentage assumption, which comes from the literatures. It is followed by the calculation for mass flow rate, molar flow rate, and then identifying the limiting reactant, and at last the best flow rate of the product. As we can see here, the component composition for both liquefaction and gasification products is obtained from the literature. Liquefaction produces gas, oil, and char, while the gasification produces the four main gases used for the production of methanol and acetic acid, which is hydrogen, carbon monoxide, carbon dioxide, and methane. The percentage conversion for each gas is shown as below. As for methanol production, methanol is produced from carbon monoxide and hydrogen using the formula shown. 1 mole of carbon monoxide reacts with 2 moles of hydrogen to produce 1 mole of methanol. Assuming 80% conversion for both reactants, referring to the literature, the mass flow rate of carbon monoxide reactor is calculated by multiplying it with the efficiency. Next, the molar mass of carbon monoxide is used to calculate the molar flow rate of carbon monoxide. These steps are followed to calculate the mass flow rate of hydrogen, followed by the molar flow rate of hydrogen. From the values obtained, it can be found that carbon monoxide is the limiting reactant. Hence, 1 mole of carbon monoxide produces 1 mole of methanol, and therefore 5,452,720 kmol per year of carbon monoxide produces the same amount of methanol, since the equation relation is 1:1. Molar mass of methanol, which is 32 kg per kilomole, is used to calculate the mass flow rate of methanol produced, which is equals to 174,487 tons per year. This is the value for our product for this plant design project. For manual calculation for acetic acid production, Acetic acid is produced from the reaction between carbon dioxide and methane as shown in the figure. Assuming 95% conversion for both the reactants, mass flow rate of carbon dioxide reacted is calculated, followed by the molar mass of carbon dioxide and then the molar flow rate of carbon dioxide. These steps are used to calculate the mass flow rate of methane that has reacted, followed by the molar flow rate of methane that has reacted. These two values are compared to find the limiting reactant. From the calculation, carbon dioxide is found to be the limiting reactant for this process. 1 mole of carbon dioxide produces 1 mole of acetic acid. Therefore, 1,209,558 kmol per year of carbon dioxide produces the same amount of acetic acid as the equation relation is 1 to 1. The molar mass of acetic acid, which is 60 kg per kilomole, is then used to find the mass flow rate of acetic acid. Hence, 72,573 tons per year of acetic acid is produced as the product of this plant.
Assalamu alaikum and very good morning. I am Usaid and I will be presenting about heat integration part in the plant design project. The importance of heat integration part is that it is used to minimize the utilities being used in the plant, as well as to maximize the energy recovery, and this will result at the end for the cost to be reduced, or to check the efficiency of the cost after applying heat integration to the plant. To carry the heat integration part, we need to implement a pinch analysis, which can create a possibility and potential of recovering heat, which can be further developed and analyzed so that we can get the optimal feasible design for the plant. The main stages involved in the pinch analysis are four. First, the streams will be selected and extracted from the PFD, and the data can be taken from the simulation software, which is Aspen Plus in our case. Then after that, the delta Tmin will be selected, composite curve and current composite curve will be constructed accordingly, and at the end the heat exchanger network will be developed. This is the process flow diagram, where we can see that some utilities exist here, like this one, and some other utilities, but after the heat integration we can see where are the feasible matches where we can connect to utilities and make a heat exchanger instead of using the utility itself, using supply like hot water, or using air for heating or for cooling. For stream selection, there are two types of stream: hot stream and cold stream. When it is from high temperature to low, it's considered as hot stream, or else it is from low temperature to high, considered as cold stream. Here in this table we can see the streams numbers as it is labeled here. This is the number of streams in the process flow diagram. The data all are taken from the Aspen Plus simulator, which is needed to conduct our pinch analysis. For delta Tmin selection, these are the list of delta Tmin according to the industry, and in our case, as we have methanol and acetic acid, which are categorized under chemical and petrochemical, we have selected 20 degrees Celsius to be the delta Tmin. This is the problem table algorithm being conducted using Hint software to identify the minimum heat required for hot streams, as well as minimum heat required for the cold streams. Also, we can see that the pinch temperature is 290, where the heat is 0, and QC min is 1722, and the QH min equal to 517.5 kilowatt. These are the hot and cold composite curves being generated automatically using Hint software. We can see that the pinch temperature is placed as at the lowest distance between hot and cold streams, particularly in this area. And also the heat recovery is around 8,277.73 kilowatt from this point to this point. At the end of the hot stream and at the beginning of the cold stream is the heat recovery area. This is the ground composite curve generated automatically using hint software. You can see that the pinch temperature at heat duty equal to 0, and the area above the pinch temperature called above pinch, and the one below it's below pinch. This is the heat exchanger network established using hint software. This area considered as the below pinch and this one as above pinch. For below pinch, the main rule is that the CP for hot stream should be higher than cold stream, so that it is considered as feasible matching, and we can get the heat exchangers number 1 and number 4, and the remaining heat will be supplied using cooler utility to reduce the temperature into the targeted temperature. For the above pinch, the rule is the opposite, the other way around. The CP should be lower for hot streams to get feasible matches with the cold streams. We can see that for this heat exchanger, the CP is 10 and for hot stream, and for the cold stream is 19, so it is considered as a feasible match. And also again, for the remaining heat, it can be supplied using a heater. Here we can see also the QH min is 517, and also the QC min, it will be 1722 if you combine C6 and C7. These two tables summarize the heat integration efficiency. Here we can see the reduction, the duty reduction, and also for hot utilities, and this is for cold utilities. Also, after heat integration, we can see that there are 3 heat exchangers added and heaters was reduced, whereas the coolers remain the same number, but the duty was reduced. This is the process flow diagram after heat integration being implemented. We take one example. This heat exchanger can exchange heat with this heat exchanger according to the heat exchanger network mentioned previously, but for the product it required more heat to reach the targeted temperature before entering the reactor. That's why we use here another utility, so that the product can reach the targeted temperature before entering the reactor. So this is the main objective of using a heat integration, to get the optimal design where we can reduce the cost and maximize the energy recovery, as well as minimize the utilities being used in the plant design.
Next, we shall move on to the chemical process control and instrumentation section. Process control of a chemical plant is needed to ensure safe operating parameters while being able to maximize production performance by minimizing disturbances, as stated by Robin Smith in his book titled Chemical Process Design and Integration. No different from this plant, chemical process control and instrumentation is a necessity for the production of methanol and acetic acid from plastic waste. There are various chemical process strategies that can be used to manipulate the parameters of a unit equipment. That include feed-forward control, which is used to anticipate disturbances and correct them. Then there is feedback control, which makes corrections after deviation is detected. Besides that, there is also cascade control, whereby there are control loops within control loops for multiple and simultaneous parameter manipulation. And finally, there is ratio control that is normally used for blending processes, as it controls streams based on ratios. However, for this project, our main focus will be on feedback control, which is used primarily for the equipments in this process, as shown in this example here. There will be 2 main equipments, the methanol reactor and a pressure swing adsorber, that we will be using and discussing as examples to showcase the controllers. Firstly, the methanol reactor, as shown here, is fitted with 3 types of control measures that manipulate the temperature, pressure, and level parameters. From the figure, you can see the inlet valve will control the level within the unit, while the compressor will be used for the pressure, And finally, the heat exchanger is used to manipulate the temperature. These are all being controlled by the controllers. Next, for the pressure swing adsorber, it works similarly to the methanol reactor in that we have similar control methods as the methanol reactor. Moving on, with any chemical plant, piping and instrumentation diagram plays a crucial part to describe the nature of a process, including the details of the major and minor equipment, the instruments, and the piping information. This P&ID shows the control measures from the beginning of the process with the pre-treatment process to the point where methanol and acetic acid is produced. In addition to the control measures mentioned earlier, pressure relief valves are also installed in all major equipments to prevent any pressure-related incidents. Lastly, this slide shows the stream data for each parameter with a total of 42 streams included into the piping and instrumentation diagram.
Good day. Now, I would like to further explain on the potential economic evaluation. To determine the detailed economic evaluation, preliminary economic evaluation is calculated using the production rate of methanol and acetic acid from the preliminary mass balance. This economic evaluation is the direct relationship between the price of raw materials needed with the price of product in the form of EP1. Assuming the plant operation is for 330 days with 24 hours operation per day, the EP1 is calculated. The EP1 is equated as the total product price minus the total raw material price and multiply with the basis, and hence EP1 is determined as Rm 398 million per year. The next step is to determine EP2, where EP1, which was calculated earlier in the preliminary economic evaluation, is subtracted with the cost of utilities that is used in the production. So from the calculation of EP2, it can be deducted that the EP2 value is in positive, which denotes that the economic feasibility is logic.
There are three nodes that have been chosen, which are the gasifier, reactor, and adsorber. For node number 1, it has been analyzed at the gasifier. For the temperature, the guide word used is more and less. The deviation for more is high temperature occurs in the gasifiers. Causes: because of extra heat from stream inlet, external heat source, failure of steam inlet control valve. Consequences of these are high product of syngas, pressure will build up in gasifier, and unstable reaction. The action required for this deviation is periodic maintenance of the control valve is required. Install temperature controller, frequently check the temperature, and install relief valve. For the parameter pressure, there is two guide words which are more and less. The deviation for more, high pressure in gasifier. It caused by thermal overpressure, incorrect pressure setting, blockage at the outlet pipe, and control valve fail to close. The consequences is unstable reaction, pressure acts on the tank wall, low yield of syngas, explosion of gasifier. Action required: frequent checking on the pressure setting, install relief valve, and periodic control valve maintenance. The parameters of this node is basically the same such as node number 1. For node number 3, the node is studied at the separator. The additional parameter, which is level, is used in this node. The guide word is more and less. For the guide word more, the deviation is high level of liquid or feed mixed gas. It caused because of leakage at control valve setting, and cross connection on pumps. The consequences of this deviation is unfinished separation process, low yield of carbon monoxide, and high amount of mixed gas accumulated in separator. The action required is install alarm systems for level. Next is frequent checking on level and install level indicator. There are a few aspects that are being considered for the plant layout. These are the aspects: separation distance, approach to the nearest assembly point, wind direction, and block segregation based on risk level. In this figure, the plant is segmented into process area at west side of the plant and non-process area at the east side of the plant. Locating the process area on the west side ensures the staff receive fewer negative consequences from plant emissions, since the wind direction is directed towards south and southeast. Flare stack is also placed to burn off the flammable gas produced during unplanned trips in the plant. Allocating 2 assembly points ensures the safety of the staff during emergency, and each of the points situated at 2 different locations of the plants. A control room beside the engineering office provides an easy access for engineers to maintain plant operation and eases in the engagement of operators with the plant engineers. The loading and unloading bay should be an easy access on road from storage location for products and raw materials.
In conclusion, this design for this plant design project is profitable for the production of methanol and acetic acid. Next, the reduction of hot utilities and cold utilities to a higher percentage can be seen after the implication of heat integration knowledge, which is the pinch analysis technique. Next, the best process selected for methanol production is from carbon monoxide and hydrogen, while the best process for acetic acid is from carbon dioxide and methane. The main aim of this project is to reduce the greenhouse gases and thus protect the environment. As for the recommendation to improve this project, getting full access to market analysis report would be helpful to obtain more accurate calculations for the profit and prices. Next, the combination of unique type of reactors or separators can be proposed for this plant design instead of just referring to literature.